This is our audio video visually impaired presentation for physical properties in molecular structure, the chapter of physical chemistry. And this chapter is from the book that is Pradeep's Physical Chemistry, Volume 3, written by Dr. S.C.K. Tripal and Pradeep Publications, Jalandhar, India. So let us start this audio video presentation. So the various methods used for the study of molecular structure may be broadly classified into the following two types. Methods based upon the study of physical properties of substances such as molar refraction, paracore based upon surface tension, optical activity, magnetic susceptibility, spectroscopic methods such as rotational and vibrational spectroscopy, microwave and infrared spectroscopy, electronic spectroscopy, UV and visible spectroscopy, Raman spectroscopy, and NMR spectroscopy. Study of molecular structure on the basis of physical properties is based upon the fact that the physical properties listed above are additive as well as constitutive. An additive property of a molecule is defined as the property, the total volume of which is the sum of the values of its constituent atoms. A constitutive property of a molecule is defined as that property which depends upon the constitution of the molecule, that is, arrangement of atoms within the molecule and the presence of multiple bond rings present in the molecule. Spectroscopic methods have already been discussed in chapter 3. Now, in this chapter, we shall take up a brief discussion of three important physical properties, namely optical activity, dipole moment, and magnetic susceptibility one by one. Optical activity, that is plane polarized light. If a ray of light travels in any direction, it has vibrations in all directions at right angles to the path of propagation. If this light is passed through Nicol prism, a Nicol prism device by the scientist Nicol consists of two prisms joined together as shown in figure 5.1 on next page. Each of these prisms is made up of a substance called Iceland spar or calcite, which is mainly calcium carbonate. If a single prism is used, it's found that two beams of light come out, each of which is a plane polarized light, and the planes of two are at right angles to each other. By comparing with second prism, one of the beams undergoes total internal reflection and only one plane polarized beam comes out. Instead of Nicol prism, a Polaroid is also sometimes used. It consists of a film of cellulose acetate mounted between the two glass plates. So, then the light emerges out of the prism is found to have vibrations in only one plane. This light is called plane polarized light. The Nicol prism thus used is called a polarizer. Optical activity. The plane of polarized light is passed through a plate of quartz or turpentine oil or the solution of sugar taken in a glass tube. It's found that in the light that comes out, the plane of the polarized light gets rotated. The substances like quartz, sugar, which rotate the plane of polarized light are called optically active. And the property of a substance to rotate the plane of polarized light is called optical activity. The substances which rotate the plane of polarized light to the right are called dextrorotatory. Dexter means right, and those which rotate the plane of polarized light towards the left are called levorotatory. Levos means left. The method of observing the rotation of plane of polarized light is based upon the following principle. If the plane of polarized light is passed through another Nicol prism which has its axis parallel to that of the first Nicol prism, the light passes through and brightness is observed through the eyepiece. On the other hand, if the second Nicol prism is placed with its axis at right angles to that of the first prism, called crossed position, the light is completely cut off and the field of view in the eyepiece is dark. At all other positions, the brightness is less, but there may not be complete darkness. It's observed that if the two Nicol prisms are set at the cross position, so that the field of view is completely dark, and then the optically substance is placed between the two arms prisms, the field of propagation of light view becomes sometimes bright. The second prism has to be rotated through certain angle about the line of propagation of light to get complete darkness again. This clearly shows that after passing through the optically active substance, the plane of polarized light has been rotated. The degree of rotation depends upon the rotation required to be given to the second Nicol prism to get the darkness again. This just as the first prism polarizes the light and is called the polarizer, second prism analyzes the light and is called analyzer. Specific rotation, the angles in degrees through which the plane of polarized light is rotated on passing through the solution of an optically active substance depends upon the following factors: nature of the optically active substance, concentration of solution in gram per ml, length of the solution, that is the length of tube through which the light passes in decimeters, Wavelength of the light used that is on the temperature of the solution. Thus, if m grams of the substance are dissolved in Vml of the solution, so that concentration of solution is m by V gram per liter. L is the length of the tube in decimeters and alpha is the angle of rotation in degrees. Then it is found that alpha proportional to concentration gram per ml, length of the tube in decimeter. Therefore, alpha proportional to m by V and in L. So alpha is equal to alpha ml upon V, where alpha T lambda is a constant characteristic of the nature of substance and depends upon the wavelength lambda of light used and the temperature of solution T degrees Celsius. If D line of sodium vapor lamp is used and the temperature of solution is 25 degrees Celsius, then it is written as alpha 25 degree D. This constant is called the specific rotation of substance. Thus, from the above equation, alpha T lambda is equal to V alpha upon Lm. If m is equal to 1, V is equal to 1 ml and L is equal to 1 decimeter, then alpha T lambda is equal to alpha, and specific rotation of a substance may be defined as the angle of rotation produced when 1 gram of the substance is dissolved in 1 ml of the solution, that is concentration of solution is 1 gram per ml, and the length of the solution through which light passes is 1 decimeter. In all reported values of alpha T lambda, the concentration of solution is taken in grams upon 100 ml of the solution. Thus, if C grams are dissolved in 100 ml of the solution, then we may put M is equal to C and V is equal to 100. This gives from equation 2. Further, therefore alpha T lambda is equal to 100 into alpha upon LC for solutions. Further, if instead of solution substance taken is a pure liquid or a pure solid, then m by v is replaced by density d of the pure substance. This gives from equation 2 alpha T lambda equals to alpha upon LD for pure liquids or solids. In case of pure solid, L is taken as the thickness of the solid in decimeter. Fourth is molar rotation. The molar rotation is obtained by multiplying the specific rotation with the molecular weight m of the substance and dividing the result by 100 to reduce the magnitude of number. It's usually represented as mt lambda. Thus, mt lambda is equal to m alpha T lambda upon 100. Measurement of optical activity, that is the angle of rotation. The instrument used for the measurement of amount of rotation in degrees caused by an optically active substance to the plane of polarized light is called a polarimeter. The principle of this instrument has already been discussed. It consists essentially of two nickel prisms, one called the polarizer and the other analyzer. Both of these are fitted on the opposite ends of the same metal tube. However, the polarizer is fixed, but the analyzer can be rotated about the axis of tube. In between the polarizer and the analyzer, there is a space for keeping the glass tube containing the solution. The glass tube is usually 5 cm, 10 cm, 20 or 25 cm and has glass windows on both ends. A circular scale is fixed on the metal tube near the analyzer. In the procedure, first of all, the monochromatic light passes from a suitable source, usually sodium vapor lamp, is passed through the instrument without placing the tube containing the liquid or the solution. The light emerging out of the analyzer is viewed through the eyepiece. The analyzer is then rotated slowly till the field of view is completely dark. This gives the initial reading of instrument. Now the tube containing the solution or the liquid of the known concentration is placed and shutter closed, not shown in figure 5.3. On seeing through eyepiece, the field of view is no longer found to be dark. The analyzer is rotated slowly till the field of view is completely dark again. This gives the final reading. The difference between the final reading and the initial reading gives the angle of rotation alpha. If it comes out to be positive, the substance is the exterior rotatory, and if negative, it is levo rotatory. Modern instruments have numerous improvements over the simple type. However, the basic principle remains the same. Optical activity and chemical constitution. Optical activity is a purely constitutive property. It depends upon the arrangement of atoms within the molecule. It has been observed that the organic compounds which are found to be optically active contain at least one carbon atom to which four different atoms or groups are attached. Such a carbon atom is called an asymmetric carbon and is usually shown by putting a sign of star over it. A very simple example of such a compound is that of lactic acid as represented below. Quite often the instrument is used for finding the concentration of sugar solution from a measured value of alpha and known value alpha and using the formula given equation 3 in section 5.2.1. The instrument used is called saccharimeter. It is found that such a compound exists in two forms, out of which rotates the plane of polarized light to the right and is called the dextero rotatory, and the other form which rotates the plane of polarized light to the left is called levo rotatory. The two forms have the same constitution in each form. The asymmetric carbon is attached to the same four atoms or groups but differ in configurations, that is, arrangement of atoms or groups in space. As the two forms are space isomers called optical isomers. Libel and Van Hoff pointed out the differences in the two forms by suggesting that in case of such molecules, the asymmetric carbon atom is present in the center of a regular tetrahedron, and the four atoms or groups attached to it are present at the corners of a tetrahedron. This gives rise to the two different spatial arrangements, which were like the mirror images of each other. Special difference in D and L forms of lactic acid. Above two configurations are different in the sense that they are not superimposable over each other. Thus, the two forms are related to each other as the right hand is to the left hand of the same person. Above two forms may be represented in a simplified way as follows. In Form 1, the arrangement from H2OH is clockwise, and Form 2, the arrangement from H2OH is anticlockwise. Hence, if one of them is dexterorotatory, the other is levo. However, by mere inspection of the configurations, it's not possible to predict as to which form is dextero or levo. The two forms are said to be enantiomorphs, Greek enantio opposite morphi form. Further, if equimolar quantities of two forms are mixed together, the third form is obtained, which is optically inactive. This is obviously due to the fact that the rotation caused by one form to the right is nullified or compensated by the equal rotation caused by second form to the left. This process is called external compensation, and the substances thus obtained are called racemic mixtures, or DL form or plus minus form. This form can be represented into D and L form by suitable methods. In case of compounds containing two asymmetric carbon atoms, that is tartaric acid, a fourth form is also found to exist. In this form, the rotation caused by half of the molecule is compensated by the other half within the molecule as shown for tartaric acid. This form, which is optically inactive due to internal compensation, is called the mesoform. Lastly, it may be mentioned that optical activity is found not only in the organic compounds containing an asymmetric carbon atom, but also in the compounds which contain other asymmetric atoms like nitrogen, sulfur, silicon, cobalt, tin. Further, some compounds may not contain an asymmetric atom but are optically active because the molecule as a whole is asymmetric, that is, no plane can divide the molecule into two identical halves. Thus, it may be concluded that the optical activity is a property related with asymmetry of the molecules, hence, optical activity can be used to test the presence of asymmetry in the molecule. Now, coming on to section 5.3, that is dipole moment, general introduction, polar and non-polar covalent bonds. A covalent bond is formed by the mutual sharing of electron between the two atoms. If the two atoms are identical, that is in H2Cl2, the shared pair of electrons is attracted equally by both the atoms and hence it remains exactly in the center of the two atoms as shown below. In HH, exactly in the center, in Cl exactly in the center. Thus, neither of the two atoms in such molecules acquires positive or negative charge. Bond is formed between two identical atoms is called a non-polar covalent bond. On the other hand, if the two atoms are dissimilar, that is in the HCl molecule, chlorine atom is more electronegative than the H atom. Hence, the electron pair is more attracted towards the chlorine atom than towards the hydrogen atom. In other words, the shared pair of electron is more displaced towards the chlorine atom over hydrogen. As a result, the chlorine end of the molecule acquires a slight negative charge, while the hydrogen end of the molecule acquires a slight positive charge. The bond thus formed between the two dissimilar atoms having slightly different electronegativities is called a polar covalent bond, and the molecule is called a dipole because it has a developed positive and negative poles. Thus, the situation is in HCl may be represented as shown. Dipole moment of a diatomic molecule. The extent of polarity or polarization of a molecule is expressed in terms of dipole moment, which is defined as follows. The dipole moment of a polar diatomic molecule is the product of the charge on each end of the molecule and the average distance between the centers of their nuclei, that is the bond length. In general, for a polar diatomic molecule, that is AB, in which atom B is more electronegative than A, plus Q is the charge on the end A and minus Q on the end B of the molecule, and D is the average distance between the centers of their nuclei, then the dipole moment of the molecule AB is given by mu is equal to Q into D. Obviously, if the molecule is non-polar, that is Q is equal to 0 and hence mu is equal to 0. Units of dipole moment. The charge present on the ends of the molecule is usually of the order of 10 to the power minus 10 ESU, and the distance between the atoms, that is bond length, is usually of the order of 10 to the power minus 8 centimeter in angstrom units. Therefore, mu must be of the order of 10 to the power minus 10 into minus 8 is equal to 10 to the power minus 18 ESU centimeter. This value is called the 1 dBi after the name of pioneer worker in this field. 1 dBi is equal to 10 to the power minus 18 ESU centimeter. Vector nature of the dipole moment. The dipole moment is a vector quantity. It has both magnitude as well as direction. It is therefore represented by an arrow pointing from the positive end to the negative end of the molecule. Fifth, the dipole moment of a polyatomic molecule. In a polyatomic molecule containing more than two atoms, every two bonded atoms have their dipole moment. This is called the bond moment. The net dipole moment of a polyatomic molecule is the resultant of the different bond moments. Obviously, the resultant will depend upon the directions of the bonds. Thus, if a molecule AB2 contains two AB bonds at an angle of theta and mu AB is the value of each bond moment, then the dipole moment of the molecule will be mu is equal to 2 mu AB cos theta star by 2. For a general molecule ABC with the two ends AB and AC having bond moments mu1 and mu2 and inclined at an angle of theta, the dipole moment of the molecule by parallelogram law will be mu is equal to root under root mu1 square plus mu2 square plus 2 mu1 mu2 cos theta, or it may be calculated graphically. As mu is known from the experiments, therefore knowing the value of theta, the method is usually used for the calculation of bond moments. Alternatively, knowing the value of mu and mu b, the method can be used for the calculation of theta and hence for predicting the shapes of molecules as discussed later in the section. The experimentally observed values of dipole moment of some common molecules and the calculated values of some common bonds are given in the table. For H2, Cl2, bromine, iodine, nitrogen, mu is equal to 0. For CO2, CS2, SnCl4, SnI4, mu is equal to 0. For HCl, 1.03, HBr, 0.78, HI, 0.38, H2, 1.84, NH3, 1.46, H2S, 1.10, SO2, 1.63, N2O, 0.17, CO, 0.12, pH, 3.55, PCl, 3.78, HCN, 2.93. For CH4 aliphatic, C2H6, C2H4, C2H2, mu is equal to 0. For CCl4, CBr4, mu equals to 0. CH3Cl 1.86, CH3Br 1.80, C2H5Br 2.03, CH3OH 1.78, C2H5OH 1.85, and CH3NH2 1.24, CH3COH 1.74. Aromatic, chlorobenzene 1.73, bromobenzene 1.71, iodobenzene 1.20, nitrobenzene 4.23, aniline 1.56, phenol 1.70, p-dichlorobenzene equals to 0, m-dichlorobenzene 1.72, oak dichlorobenzene 2.50. And bond moments for HC, bond moment is 0.2, HN 1.5, HO 1.6, HF 0.2, HP 0.55, HS 0.8, HCl 1.03, HF 2, HCl 1.03, HBr 0.78, HI 0.3738, CCl 1.7, SCBr 1.6, CI 1.4, PCl 1.8, PBr 1.6, CO 0.9, C double bond O 2.5, C triple bond O 5.3, CN 0.4, CS 1.2, C double bond S 3.2, NO 1.9. The resultant dipole moments of the groups like NO2, NH2, CH3 have also been reported. These are called group moments. Their values depend upon whether the group is attached to an alkyl radical or an aryl radical. The values of a few groups are given below. Group moment in alkyl X minus 3.05 nitro minus CN for 3.46 CH3 plus minus 0 minus NH2 plus 1.23. Group moment in ARX minus NO2 3.93 minus CN 3.99 minus CH3 plus 0.45 minus NH2 plus 1.55. A negative value of group moment means that the group is more electronegative, and a positive value means that the group is less electronegative than the alkyl or aryl group, that is benzene ring. Electrical polarization of the molecules. Every molecule is made up of a positively charged nuclei and negatively charged electron cloud as shown. The center of positive charge coincides with the center of negative charge. Hence, when such a molecule is introduced between the two poles of an electric field, the positively charged nuclei and hence the center of positive charge is attracted towards the negative plate, whereas the negatively charged electron cloud is attracted towards the positive plate of the electric field. As a result, the molecule gets distorted as shown. This is called polarization of the molecule, and the distorted molecule with positive and negative ends is called an electric dipole or dielectric. The molecule remains polarized so long as the electric field is applied but goes back to the original state as soon as the electric field is switched off. That is why this type of polarization is called induced polarization, and the electric dipole formed is called the induced dipole. Since even after polarization, The molecule is neutral as a whole. This means that the positive charge on one end must be equal to the negative charge on the other. Suppose this charge is q. If t is the distance of separation between the charges, the dipole moment of the induced dipole, called the induced dipole moment, represented by mu I, will be given by q into d. Evidently, the value of mu I will depend upon the nature of molecule and the strength of electric field. Say x, we write mu I is equal to alpha into x, where alpha is a constant and is called polarizability of the given molecule. Alpha is further found to be related to the dielectric constant d of the medium present between the plates, that is, the molecules being studied according to the equation put forward by Clausius and Mosotti. D minus 1 upon d plus 2m upon rho is equal to 4 by 3 pi n alpha, where m is molecular mass of the molecules, rho is density of the molecules, n is Avogadro's number. Now, Clausius-Mosotti equation. Suppose an electrostatic field is applied to two plates so that they are charged. Suppose the strength of uniform electric field present between them is E naught. Now, if a non-polar medium is placed between the plates, that is, the strength of electric field will be reduced to E, because the induced dipole called the dielectrics act in opposition to the applied field and hence partially neutralize the charges of plates as shown. Ratio E naught by is called the dielectric constant d, or relative permittivity of the medium. From electrostatics, it can be shown that E naught is equal to E plus 4 pi I, where I is the induced dipole moment per unit volume, that is I is equal to mu I into n, where mu I is the induced dipole moment in a single molecule and n is the number of molecules per centimeter cube. So dividing both sides of equation 4 by E and putting E naught by E is equal to d, we get d is equal to 1 plus 4 pi I by E, or d minus E is equal to 4 pi I. D minus 1 E is equal to 4 pi I. Intensity of the electric field strength X acting on each molecule is calculated by supposing that a unit charge is enclosed in a small spherical cavity, which is large as compared with the size of molecule but small in comparison to the distance between the plates. This electric intensity is then made up of the following parts. That is, the field strength of the charges on the plates, the charges induced on the surfaces of dielectrics in contact with the plates, that is minus 4 pi I, charges induced on the surface of spherical cavity plus 4 by 3 pi I. So x is equal to E naught plus 4 by 3 pi I minus 4 pi I. Substituting the value of E naught from equation 4, we get x is equal to E plus 4 by 3 pi I. Substituting the value of 4 pi I from equation 5, it becomes x is equal to E plus d minus 1 upon 3e. So 1 plus d minus 3e equals to d plus 2 by 3e. E plus 4 by 3 pi is equal to d plus 2 upon 3e. So d minus 1 upon 3e is equal to 4 by 3 pi I. Putting I is equal to mu I into n. So alpha x into n. So alpha d plus 2 by 3 en. So equation 9 becomes d minus 1 upon 3 e is equal to 4 by 3 pi n alpha d plus 2 by 3e into n. D minus 1 upon d plus 2 equals to 4 by 3 pi n alpha. If rho is the density of substance placed between the charge plates, that is of the medium between the charge plates, and m is its molecular mass, then molar volume of the substance is equal to m by rho. If n represents Avogadro's number of molecules per unit volume, that is n is equal to n upon m by rho, n rho by m. Substituting this value, d minus 1 upon d plus 2 is equal to 4 by 3 pi n rho upon m alpha. So d minus 1 upon d plus 2 m by rho is equal to 4 by 3 pi n alpha, as all quantities on the right hand side of the equation 12 are constant, alpha being constant for a given substance independent of temperature. Therefore, the quantity on the left hand side of equation 12 must also be constant, independent of temperature and depending only upon the nature of molecule. This quantity is called molar polarization and is represented by P. Further, as the applied field produces an induced charge in the molecule by the relative displacement or distortion of electrons and nuclei, P is often called induced or distortion polarization and is represented by Pi or Pd. Thus, Pi or Pd is equal to T minus 1 upon d plus 2m by rho. Induced molar polarization is defined as the amount of polarization produced in 1 mole of the substance when placed between the plates of electric field of unit strength. From equation 13, it is evident that the units of Pi will be same as that of m by rho, that is molar volume. Hence, Pi is usually expressed in centimeter cube upon mole. Expression 13, giving the relationship between dielectric constant and polarizability, was first derived by Mosotti 1850, Clausius 1879, and is called Clausius-Mosotti equation. Effect of temperature on polarization. Using equation 13, the value of molar polarization have been determined for a number of substances. It's found that whereas molar polarization of number of substances such as O2, CO2, N2, and CH4 are constant and independent of temperature, the polarization values for some other substances such as HCl, CHCl3, C6H5, and NO2, CH3Cl do not come out to be constant but decrease with increase of temperature. This observation has been the basis of the measurement of dipole moment in the study of molecular structure as explained below. In case of molecules such as HCl, HCl3, their centers of positive and negative charges don't coincide with each other, thus they possess some dipole moment even in the absence of electric field. The dipole moments thus possessed by the molecules is called permanent dipole moment. In the absence of electric field, these permanent dipoles are oriented in a random manner due to thermal agitation as shown. However, in the presence of electric field, two disturbing effects takes place. These are the electric field will tend to rotate and orient these dipoles in the direction of field, and the electric field will tend to polarize the molecules. If the molecule were stationary, the dipoles would have been oriented perfectly parallel to the electric field, that is at right angles to the plates of electric field. However, due to thermal agitation, they take a position in between that of the original state and the perfectly parallel state as shown at P in figure for any permanent dipole. Thus, in case of molecules possessing permanent dipoles, the right-hand side of equation 13 will give the total polarization Pt, which will be sum of the induced molar polarization Pi and the orientation molar polarization Pt is equal to d minus 1 upon d plus 2m by rho is equal to Pi plus P no. As mentioned earlier, the induced polarization is given by Clausius-Massotti equation. Pi is equal to 4 by 3 pi n alpha. Orientation molar polarization is given by the equation put forward by d by Po is equal to 4 by 3 pi n mu square upon 3 kt, where mu is the permanent dipole moment of the molecule, k is Boltzmann constant, R upon n. T is the temperature. Substituting the values of Pi and Po from equation 15 and 16 in equation 14, we have Pt is equal to d minus 1 upon d plus 2m by rho is equal to 4 by 3 pi n alpha plus 4 by 3 pi n mu square upon 3 kt. So measurement of dipole moment. First is the vapor temperature method. The above equation can be written in the form Pt is equal to A plus B by T, where A is equal to 4 by 3 pi n alpha and B is equal to 4 pi n mu square upon 3k are constant for the given substance. This equation is primarily applicable to gaseous and vapors. Thus, if Pt is plotted against 1 by T, a straight line graph will be obtained if the molecules possessed permanent dipoles. The slope of the plot will be given by B is equal to 4 pi n mu square upon 9k. From this equation, the permanent dipole moment mu of the molecule can be calculated as all other quantities are constants whose values are known. Solving equation 19 by putting the values of various constants, we get mu is equal to 0.0218 root p into 10 to the power minus 18. The straight line plots for a few substances with and without permanent dipoles, that is polar and non-polar molecules, are shown in 5.13 figure. It may be seen that whereas Pt varies with temperature, in for HCl and CH3Cl possessing permanent dipoles, there is no effect of temperature on substances like CH4, CCl4, which don't have permanent dipoles and hence possess only induced molar polarization. Now, method of measurement of dipole moment. As explained above, the basic equation for the determination of dipole moment is Pt is equal to d minus 1 upon d plus 2m by rho is equal to A plus B by T, where A and B are constants with B is equal to 4 pi n mu square upon 9k. Thus, the experiment involves the determination of dielectric constant d and the density rho of the different rho at the different temperatures. The values of Pt are then calculated and plotted against 1 by T. If Pt is found to be varying linearly with 1 by T, the substance possesses a permanent dipole moment, and the value of the dipole moment mu is calculated from the slope of the line. On the other hand, if Pt is found to be independent of temperature, the substance doesn't possess any permanent dipole moment, that is, it's non-polar. Dielectric constant required in the above equation is determined by first measuring the capacity of a condenser in vacuum between the plates C naught and then measuring the capacity of same condenser when filled with the given substance. The dielectric constant of a given substance is then given by d is equal to C by C naught. Refraction method. According to Clausius-Massotti equation, the induced or distortion molar polarization Pi or Pd of the molecules is given by d minus 1 upon d plus 2 m upon rho is equal to 4 by 3 pi n alpha. As d dielectric constant is a pure number, molar polarization P is simply molar volume of the material. Further, it has already been explained that it is independent of temperature if the substance is non-polar and makes doesn't have a permanent dipole moment. For such molecules, it was derived by J.C. Maxwell 1881 that the dielectric constant of a substance is related to its refractive index for light of long wavelength according to the equation. So D is equal to n infinity square. Substituting this equation 22, PD is equal to n infinity square minus 1 upon n infinity square plus 2 m by rho is equal to 4 by 3 pi n alpha. However, n infinity square cannot be found by extrapolation to infinite wavelengths. The value of refractive index is measured with visible light. This is because visible light can displace only electrons, whereas the positively charged nuclei remain unaffected. Thus, the distortion polarization can be considered to be sum of the electron polarization P and atom polarization Pa. Therefore, Pd is equal to Pe plus Pa. Polarizability alpha is also accordingly made up of two parts, that is alpha E, called electron polarizability, and atomic or nuclear polarizability alpha A respectively. Now, to find the value of Pd, it's therefore necessary to measure the refractive index using infrared rays because they can displace the heavy atomic nuclei as well as electrons, but measurement of refractive index with infrared radiations are difficult. Hence the problem is resolved by finding electron polarization by P is equal to n square minus 1 upon n square plus 2m by rho. As an approximation, 5% of this value is added to it to account for Pa to get the total value of Pd. That is Pd is equal to P plus Pa, which 5% of Pe. Then as before, total polarization Pt of a molecule possessing a permanent dipole moment is the sum of the two terms, the first called the distortion polarization and the second called the orientation polarization due to permanent dipole moment possessed by the molecule. So Pt is equal to Pd plus P naught, putting the value of P naught is equal to 4 by 3 pi mu square upon 3 kt. Equation 5 becomes Pt is equal to Pd plus 4 by 3 pi n mu square upon 3 kt. Putting the values of constant and simplifying, we get mu is equal to 0.0128 root Pt minus Pdt. Pt can be determined by finding the dielectric constant of vapor at temperature T, and Pd can be found either by measuring the refractive index using infrared radiation or by approximation method explained above. This method is simpler than the temperature method because it involves the measurement only at one temperature. Dilute solution method. Equation 20 is applicable to gases and vapors only. For substances which are not gases or which cannot be converted into vapors, following procedure is followed. The dilute solution of the given substance is prepared in a non-polar solvent such as benzene. CCl4CS2, that is the density dielectric constant of the solution, are determined at various temperatures. At each temperature, the molar polarization of the solution PS is calculated using the equation PS is equal to D minus 1 upon D plus 2 x1m1 plus x2m2 upon rho, where x1 x2 are the mole fractions of solvent and solute in their solution. M1 M2 are their respective molecular masses, and rho is the density of solution. That is, third, the molar polarization of solution is related to the molar polarization of solvent x1 and that of the solute x2. PS is equal to x1 p1 plus x2 p2. Thus, knowing the values of x1 x2 p1, the value of p2, that is molar polarization of solute substance being studied, can be calculated. The values of P2 at different temperatures are plotted against 1 by T. The value of mu is then calculated from the slope of line as explained earlier. Dipole moment in the chemical constitution. Applications of dipole moment. The knowledge of dipole moment of a molecule can be applied in a number of ways to study its chemical constitution. A few important applications of dipole moment are briefly described below. In comparing the relative polarities of molecules, for example, the dipole moment of HF, HCl, HBr, HI are 2.0, 1.03, 0.78 and 0.38 dBi respectively. This shows that the polar character of the molecules decreases as we move from HF to HI. In calculating the percentage ionic character of a polar covalent bond, for example, the dipole moment of HCl is 1.03 dBi. If the bonds were 100% ionic, each end would require full 1 unit charge, that is 4.8 into 10 to the power minus 10 ESU. The bond distance in HCl is taken to be 1.275 angstrom is equal to 1.275 into 10 to the power minus 8 centimeter. Hence, if HCl were 100% ionic, the dipole moment would have been 4.8 into 10 to the power minus 10 into 1.275 into 10 to the power minus 8 ESU centimeter. So that equals to 6.11 into 10 to the power minus 18 ESU centimeter. Actual value of dipole moment of HCl is 1.03 dBi. So percentage ionic character of HCl bond is 1.03 upon 6.11 into 100 is equal to 17% approximately. In predicting the geometry or shapes of molecules, the fact that the dipole moment is a vector quantity and that a particular bond has almost a constant value of bond moment is very useful in predicting the shapes of molecules. A few cases are explained below. Diatomic molecule. A diatomic molecule is always linear irrespective of the dipole moment. Triatomic molecule. In triatomic molecule of the type AB2, there are two possibilities. First, the dipole moment of the molecule may be zero, that is in case of CO2 and CS2. This shows that in these molecules one bond moment is equal and opposite to the other, since the molecules must be linear as shown, that is CO2 and SO2. The molecule may have a definite value of dipole moment, that is mu for H2 is equal to 1.84d, mu for SO2 is 1.63d. Obviously, in these cases, the possibility of linear shape is ruled out. The two bonds must have a definite angle between them, which can be calculated if we know the bond moments as discussed earlier in section. For example, the bond moment for HO is 1.60 pi. The bond angle is calculated to be nearly 105 degree, as H2O may be represented as shown. Such molecules are called bent molecules and the shape is called the V shape. C is tetraatomic molecules. In tetraatomic molecules of type AB3, the two simple possibilities are the dipole moment of the molecule may be zero, that is in BF3. In such a case, all the four atoms must be in one plane and the angles between the bonds must be equal in BF3 shown in this figure. Such a shape is called a planar trigonal. The molecule may have some definite value of dipole, that is NH3PF3 PCl3. This indicates that one atom lies out of the plane of the rest of atoms. For example, the molecule of NH3 may be represented as this. Such a shape is called a pyramidal shape. Pentaatomic molecules. The pentaatomic molecules of the type AB4, which we commonly come across, are CH4, CCl4, SiCl4, SnCl4. The dipole moment of all these molecules is found to be zero. This is possible only if these molecules have symmetrical or regular geometry so that the different bonds moment cancel out each other. Experimental facts confirm that these molecules have tetrahedral shape as represented below. In differentiating cis-and-trans isomers, the cis-and-trans isomers are represented as HCX double bond CHX. So this is cis and this is trans. The second possibility is that the atoms may be in one plane but the angle between the bond may not be equal, that is in ClF3. The shape is planar but not trigonal. It is clear that the trans form will be non-polar, that is will have a zero dipole moment, whereas cis form will be polar, that is will have a definite dipole moment. For example, in case of dichloroethene, putting X is equal to Cl, cis form has been found to have a dipole moment of 1.95. The trans form is found to have a zero dipole moment. In differentiating ortho, meta and para isomers, as benzene is a regular hexagon and its dipole moment is zero, therefore substituting two atoms or groups in the ortho, para or meta positions, the di-substituted derivatives will have different dipole moment or for the ortho, meta and para isomers as shown below. Obviously, para will have a zero dipole moment and meta will have a less dipole moment than ortho. Sixth, in supporting the possibility of resonating structures, for example, the nitrous oxide molecule N2 has a small value of dipole moment 1.17 dBi. If the molecule is supposed to have any one of the following two structures, N minus is equal to N minus double bond N plus double bond O, and this N triple bond N plus minus O negative. The dipole moment should be high. This confirms that N2 is a resonance hybrid of structures 1 and 2. Magnetic susceptibility, that is, first is magnetic permeability. If two magnetic poles of strength M1 and M2 are separated by a distance of r, then the force affecting between them is given by F is equal to 1 upon mu M1 M2 upon r square. The quantity mu used in the above expression is called the magnetic permeability of the medium between the poles. If it is defined as the relative tendency of the magnetic lines of force to pass through the medium as compared to that in the vacuum. For vacuum, mu is taken as equal to 1. Similarly, for air, the quantity mu in the above expression is called the magnetic permeability of the medium between the poles if it is defined as the relative tendency of the magnetic lines of force to pass through the medium as compared to that in the vacuum. For example, mu is taken as equals to 1. Similarly, for air, mu is taken as approximately equal to 1. Second is diamagnetic, paramagnetic and ferromagnetic. As mentioned above, for vacuum mu is equal to 1. For other media, mu can be less than or greater than 1. If mu is less than 1, then the magnetic lines of force prefer to pass through the vacuum rather than through the substance comprising the medium. In other words, the magnetic lines of force are repelled away from the substance. Such substances are said to be diamagnetic. On the other hand, if mu is greater than 1, then the magnetic lines of force have greater tendency to pass through the substance rather through the vacuum. In other words, the magnetic lines of force are attracted towards the substance. Such substances are called paramagnetic. If mu is very high, that is of the order of 10 to the power 3 or more, this sets the tendency of substance to be attract the magnetic lines of force is very high, and the substance is said to be ferromagnetic. Ferromagnetism is exhibited by mainly iron, cobalt, nickel, and their alloys. It's a property of greater interest in the subject of physics. In chemistry, we deal only with the diamagnetism and paramagnetism. The behavior of diamagnetism and paramagnetic substances in a magnetic field is shown diagrammatically. Magnetic susceptibility. As seen above, if any material is placed in a magnetic field, the strength of the magnetic field in the material is different than that in the vacuum. The strength of magnetic field thus present in the material is called the magnetic induction. If H is the strength of applied magnetic field and B is the magnetic induction in the given material, the two are related according to the equation B is equal to H plus 4 pi I, where I represents the magnetic moment per unit volume. The material and is called the intensity of magnetization. It may be positive or negative depending upon whether the material is paramagnetic or diamagnetic. The intensity of magnetization produced per unit strength of the applied magnetic field is called the specific magnetic susceptibility. It is usually represented by x, thus mathematically x is equal to y upon h. It's this quantity which is usually measured experimentally in the study of magnetic properties of different materials. Multiplying the specific magnetic susceptibility with the molar volume and of the material, we get what is called the magnetic susceptibility per mole or molar magnetic susceptibility. Is usually represented by xm. Xm is equal to pi rho I upon h. The molar magnetic susceptibility may be defined as the intensity of magnetization induced per mole of the material by the unit field strength. Quite often it is convenient to deal with the quantity xm in place of x. Further, the magnetic induction B is related to the strength and the applied magnetic field according to the equation B is equal to mu h, where mu is the magnetic permeability of the medium, that is the material placed between the poles. Also from equation 2, I is equal to xh, substituting the values of P and I from equation 4 and 5. In equation 1, we get mu h is equal to h plus 4 by xh. So mu is equal to 1 plus 4 by x. Since I in the above discussion is the magnetic moment per unit volume, therefore of the material x is in fact the volume susceptibility of the medium. However, for most of the practical purposes we use mass susceptibility. It is obtained by dividing the volume susceptibility by the density rho of the material. Hence we have mass susceptibility x dash is equal to x upon rho. X is equal to rho x dash. Mu is equal to 1 plus 4 pi rho x dash. X dash is equal to mu minus 1 upon 4 pi rho. This gives the relationship between the specific magnetic susceptibility and the magnetic permeability of a material of density rho in gram per cc. Since for diamagnetic substances mu less than 1, therefore to specify magnetic susceptibility x or x dash is negative for such substances. On the other hand, thus for paramagnetic substances mu greater than 1, therefore x or x dash is positive but small. For ferromagnetic substances, as mu is very large, so x or x dash is also very large. Magnetic susceptibilities are generally determined by the method put forward by Gues in 1889. It is shown in figure 5.2 and is briefly explained below. The material under examination is taken in the thin cylinder or a tube which is then suspended vertically with a wire from one arm of the balance between the two poles of an electromagnet such that the lower end of the cylinder is nearly in the middle of the poles of electromagnet. The cylinder is now counterbalanced in this position by placing weights in the other pan of the balance. The current is now switched on into the electromagnet. If the substance is paramagnetic, the cylinder will be pulled down so that more magnetic lines of force can pass through it. On the other hand, if the substance is diamagnetic, the cylinder will be pushed upward so that less magnetic lines of force may pass through it. In first case, some extra weight will have to be added into the pan, whereas in the second case, some weights will have to be removed from the pan to restore the balance. Since the change in weight is equal to the magnetic lines of force acting on the material, hence if delta m is the change in mass, then we have delta mg is equal to half x minus xa eh square, where g is the acceleration due to gravity, so that delta mg gives the change in weight. The right hand side is called the magnetic force acting on the material of volume susceptibility. X when A is the area of cross section of specimen, H is the field strength, and Xa is the volume susceptibility of air. Value of Xa is 0.03 into 10 to the power minus 6. Thus, using equation 9, the value of X can be calculated. In the above calculations, the absolute value of field strength H is also required. However, the necessity of measuring H and A can be eliminated if the experiment is first performed with substance of known susceptibility. using the same field strength and the same cylinder for taking this substance. Usually water is taken as a standard substance for this purpose. Then evidently as we will have delta ms upon delta mw is equal to xs minus xa by xw minus xa. The delta ms is the change in mass. The sample under examination is placed in the magnetic field, and delta mw is the change in mass when water is taken in the same cylinder and placed in the same magnetic field. Xs is the magnetic susceptibility, volume susceptibility of sample, and Xw and Xa are those of water and air respectively. Magnetic susceptibility in molecular structure. A detailed study of the magnetic susceptibilities of a large number of organic and inorganic compounds carried out by Pascal during 1908 to 1913 has revealed that, like many other physical properties such as molar refraction, paracord, the molar magnetic susceptibility is additive as well as a constitutive property. The values assigned to the various atoms and to the structural factors, double bond, triple bond rings, can be obtained from the experimentally determined values for a large number of elements and compounds. The values of magnetic susceptibilities for some of the atoms and structural groups are given in the table 5.3 below. H. Magnetic susceptibility is minus 2.93. These all are multiplication of 10 to the power minus 6. C minus 6. O minus 4.61 in alcohols and ethers. O plus 1.73 in ketones. O minus 3.36 in esters and acids. N in amine chain. In open chain minus 5.57, N 5 minus 4.67 in rings, N in 1 minus 1.54 in amines, F minus 11.5, Cl minus 20.1, Br minus 30.6, C double bond C 5.4 into 10 to the power minus 6, and N double bond N 1.9, C double bond N 8.2, C triple bond C zero point 0.8, C triple bond N minus zero point 0.8. Benzene minus 1.5. When for an aromatic compound, the value of benzene ring has been added, no value has to be added for C double bond C bond. The calculation of molar magnetic susceptibility of a compound for the atomic and structural values helps us to decide between the alternate structures for a compound or to confirm the structures of compound by comparing the calculated value with the experimental value. A few examples are illustrated below. Diamagnetic substances were studied for this purpose because their magnetic susceptibility is independent of temperature and is nearly same for substances in the gaseous and liquid states. Explanation of diamagnetism and paramagnetism. Electrons in an atom have orbital motion as well as spin motion. As they are charged particles, therefore their motion produces a small magnetic field. If all the electrons in a molecule are paired, the magnetic moment of the electron spinning in one direction is cancelled by the magnetic moment of the electron spinning in the opposite direction. Net result is that the substance has zero magnetic moment. If such a substance is placed in a magnetic field, small magnetic moment is induced in the substance in opposition to the external magnetic field. As a result, the substance is repelled by the magnetic field. This type of behavior is observed for diamagnetic substances. This diamagnetism is exhibited by those substances which contain only paired electrons, that is, no unpaired electron is present. On the other hand, if a substance contains some unpaired electrons, the magnetic moment of the electrons don't cancel out completely. Hence, the substance has a permanent magnetic moment of its own. In fact, each unpaired electron behaves like a micromagnet with a definite magnetic moment. If such a substance is placed in external magnetic moment, the micromagnets will arrange themselves parallel to the external field and the induced magnetic moment is insufficient to overcome the permanent magnetic moment of the substance. Such substances are therefore attracted by the magnetic field instead of being repelled by it. This type of behavior is observed for the paramagnetic substances. This paramagnetism is exhibited by those substances which contain some unpaired electrons. As explained above, each atom, ion, or molecule of paramagnetic substance behaves like a micromagnet with a definite inherent magnetic moment of magnitude μm. When such a substance is placed in the external magnetic field, the micromagnets tend to arrange themselves parallel to the applied field. However, this tendency is opposed by the thermal motion of particles because magnetic susceptibility of paramagnetic substances varies with temperature. Hence, the actual arrangement taken up will depend upon the temperature. Langevin in 1905 put forward the following relationship between molar magnetic susceptibility Xm, mu m, and temperature T. Xm is equal to alpha m into mu m square n upon 3 kt, where n is a Avogadro number, k is Boltzmann constant, alpha m is a constant for the given substance. It represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field. In equation 11, All quantities are constant except xm and T, thus determining xm for a given substance at different temperatures T and then plotting xm versus 1 by T. A straight line graph will be obtained, the slope of which will be equal to mu n square upon 3k, hence mu m can be calculated. The units of mu m are cos per inverse. However, it's usually expressed in terms of Bohr magnetons. Bm 1 bm is equal to 9.273 into 10 to the power minus 21 ergs per Gauss. Relationship between magnetic moment and the number of unpaired electrons. Total magnetic moment of any atom, ion, or molecule is the sum of the following two values. Magnetic moment due to orbital motion of electrons is equal to root LL plus 1 Bm, where L is the azimuthal or orbital quantum number for that electron. Magnetic moment due to the spin motion of electron is equal to 2 root SS plus 1 Bm, where S is the spin quantum number having the value equals to half. If ions or molecules are considered instead of free atoms, it's expected that the orbital motion of electrons are tied into the nuclear configuration of the molecule or the ion so tightly that they are unable to line up with the applied magnetic field. Hence, the magnetic moment contribution due to the orbital motion is negligible. Thus, the applied magnetic moment of the molecule or the ion is mainly due to spin motion of the electrons, hence it's called spin magnetic moment. Thus, we have m is equal to 2 root ss plus 1 bm, where S represented spin quantum number for one unpaired electron for a molecular ion containing a number of unpaired electrons. The expression is usually written as mu m is equal to 2 root ss plus 1 bm, where S represented the total spin quantum number. Thus, for one unpaired electron, S key value half. Two unpaired electron, S is equal to 2 by 2. For 3, S is equal to 3 by 2. In general, for n unpaired electrons, S is equal to n by 2. So mu m is equal to 2 root n plus 2 by plus 1 into n by 2. So mu m is equal to root n plus 2 bm. Thus, knowing the number of unpaired electrons present, the magnetic moment mu m can be calculated, or vice versa. The expected values of the magnetic moment mu of m for a paramagnetic substances for different values of unpaired electrons are given in table 5.4. Taking alpha m to be negligible in equation 11, as it represents the diamagnetic molar susceptibility of the substance induced by the applied magnetic field, becomes xm is equal to mu m square n upon 3 kt. Substituting the value of mu m from equation 14 in equation 15, we get xm is equal to n upon 3 kt and n plus 1 and n plus 2. So now coming on to the applications of magnetic susceptibility in confirming the structure of a given molecule. The use of molar magnetic susceptibilities in confirming the structure of a given molecule is based upon the fact that magnetic susceptibility is additive as well as constitutive property, as already discussed in section 5.4. Calculation of number of unpaired electron in a molecular ion. Knowing the molar magnetic susceptibility xm, the number of unpaired electrons present in the molecule can be calculated using 16 equation. This has helped in understanding the electronic structure of a number of molecules. For example, molar magnetic susceptibility of oxygen has been found to be 3400 into 10 to the power minus 6, which shows that it must contain two unpaired electrons. Thus, the structure of oxygen molecule should be represented as O. In the study of coordination compounds, the main application of magnetic susceptibility in chemistry has been the study of coordination compounds of transition elements. Measurement of magnetic susceptibility helps us to know the number of unpaired electrons present in the complex, which in turn helps us to assign the correct structure of the complex in the some cases. For example, the magnetic susceptibility values of the complexes FeCN6 3 negative, Fe6 3 negative, though each has the same coordination number 6, suggests that there is one unpaired electron present in the former, whereas there are 5 unpaired electrons present in the latter. These are explained by suggesting following electronic structures in these complexes and establishing formulas of certain compounds. For example, it has been shown that the formula of hypophosphoric acid is H4P2O6 and not H2PO3. This is because of the latter formula were correct. Sodium and if latter formula were correct, sodium and silver salts NaHPO3 and Ag2PO3 would contain an odd number of electrons and should be paramagnetic, while actually they are diamagnetic. Hence, their salts must have the formulas Na2H2PO2O6 and Ag4P2O6 respectively. Similarly, the formula of mercurous chloride is He2Cl2 and not HgCl in presence when explaining the existence of odd electronic species. Compound containing odd electrons are expected to be paramagnetic. This is actually found to be so for a few gaseous compounds, namely nitric oxide, nitrogen dioxide, chlorine dioxide. Moreover, their magnetic susceptibilities show that they contain one unpaired electron in each case. In explaining the formulation of free radicals, some highly substituted aromatic compounds have a tendency to dissociate into fragments called free radicals. The existence of free radicals is supported by the fact that such compounds exhibit appreciable paramagnetism, which is explained on the basis that the free radicals contain electrons, the odd electrons. The measurement of magnetic susceptibility of such substances even helps in the calculation of percentage dissociation of the substance into free radical. For example, the paramagnetic susceptibility of NL alpha N-ethyl diphenyl methyl is found to be 140 into 10 to the power minus 6. Theoretical value for a single unpaired electron 1260. Theoretical value for a single unpaired electron as shown is 1260 into 10 to the power minus 6. Hence, percentage of compound dissociated into free radicals is 140 divided by 1260 into 100 is equal to 11%. Now coming on to the final topic, dielectric properties of solids. Insulators do not conduct electricity because the electrons present in them are held tightly to the individual atoms or ions and are not free to move. However, when electric field is applied, polarization takes place because nuclei are attracted to the one side of the electrons club to the other side. Thus, dipoles are formed. In addition to these dipoles, there may be also permanent dipoles in the crystal. These dipoles may align themselves in an ordered manner so that such crystals have a net dipole moment. Such polar crystals show the following interesting electrical properties. First is piezoelectricity or pressure electricity. When mechanical stress is applied on such crystals so as to deform them, electricity is produced due to the displacement of ions. The electricity thus produced is called the piezoelectricity, and the crystals are called piezoelectric crystals. Conversely, if the electric field is applied to such crystals, atomic displacement takes place, resulting into mechanical strain. Thus, such crystals act as a mechanical electrical transducer. A few examples of piezoelectric crystals includes titanates of barium and lead zirconate, ammonium dihydrogen phosphate, and quartz. These crystals are used as pickups in the record players, where they produce electrical signals by application of pressure. They are also used in microphones, ultrasonic generators, and sonar detectors. Second is pyroelectricity. Some piezoelectric crystals, when heated, produce a small electric current. The electricity thus produced is called the pyroelectricity. Pyre means heat. Ferroelectricity. In some of the piezoelectric crystals, dipoles are permanently polarized even in the absence of electric field. However, in applying electric field, the direction of polarization changes. This phenomenon is called ferroelectricity due to analogy with ferromagnetism. Some examples of the ferroelectric solids are barium titanate, sodium potassium tartarate, Russell salt, and potassium dihydrogen phosphate. It may be pointed out here that all ferroelectric solids are piezoelectric, but the reverse is not true. Anti-ferroelectricity, some crystals, the dipole align themselves in such a way that alternately they point up and down so that the crystals doesn't possess any net dipole moment. Such crystals are said to be anti-ferroelectric. A typical example of such crystals is lead zirconate. Uses of Poe properties. The various properties of solids, as explained above, are being used in electronic and magnetic devices such as transistors, computers, telephones. So this was all about this topic. Thank you so much.